чудово. Насправді, хотів ще сказати пару слів, ще раз нагадати і наголосити на важливості проєкту групового. Це може бути, в принципі, чисто з об'єктивної точки зору, він може бути зроблений за тиждень. Оце все повністю пайплайн, пошукати дані, датасет, ну там, знову ж таки, більше залученням допомоги з нашого боку, з боку мого і пані Швай. Дані, задачу сформувати, отримати парочку моделей, подивитися метрики і все. Ну і зробити висновок, там, написати гарне таке summary на сторінку 2. Це не проблема. Але бажано, дуже заохочуємо вас долучитися до цього, бо це, так би мовити, необхідна частина курсу, насправді. От, і да, зараз я гляну по командам, по груповим. Там у нас є тільки одну команду, бачу, яка взяла сегментацію, детекцію. От. А, ні, навіть вже дві команди є. Computer Science and Visionist. Ага. О, License Plate and OCR. Всі беруть трек по перформансу. Ну, логічно. Окей, це у нас вже 8 днів злучено. На курсі 23 студенти, тому ще треба команда. Так, у нас Саша Чемаченко, ти тут, да? Ти з нами?
Так.
Можете, я просто прохання записати також в загальний список студентів, що ви вже обрали тему. Ну, це і в першу вкладочку. Просто нагадаю. Дякую. Все, супер. Тоді зараз я поширю скрін, бо я навіть розумію, що це час не шерив. Але ок. Да, в цю вкладочку. По спискам команд, да, тут, в принципі, ще дві теми, да, тут це може бути на перший погляд не зовсім тривіальна штука, але вирішити можна всі ці теми там, в рамках тижня. За великого вашого бажання, ну, там, на додатковий скор, так би мовити, можна щось там більше в глибину покопати, в перформанс або там в інференс. Реідентифікація, насправді, теж не складна штука, тому всі, хто там ще про щось сумнівається, якщо раптом, то це не проблема. З усім допоможемо, з усім підтримуємо. Головне, щоб ви тімдап, так би мовити, і розподілили задачі, проявили зацікавленість, поресерчили, поінженерили і все, в принципі. Тут насправді дуже гарний досвід і гарна практика. Але да, enough of that. We switch to English. As our course is apparently in English, and sometimes I forget. Object detection. Well, I'm not going to touch the lecture, quite obviously, because this is for the next week. This material is still hidden. I think once I explain some things, I'll unhide it and just make it publicly available if you want to get even further acquainted. But for now, what I want to do is show some of my notes, so to say, on detection. Let me just remember real quick where it is. There we go, right at the bottom. There's all the computer vision tasks related to object detection. So detectors, basically. Before that, a couple of words on the task itself. So let's go for papers with code, object detection. I'll be, right off the bat, I'll be explaining in a more practical way, not a theoretical. We'll go into theory step by step, but I'm basically giving you a very brief and quick deep dive so that you understand how it works, what's it for, and presumably what industry types use it, what are the goals, the aims for it, and so on and so forth. So object detection basically is a typical computer vision task. It exists for quite some time, and there are lots of well-known benchmarks for it, like COCO, TestDev, the Pascal VOC. These are old ones. There are some newer ones, of course. There are different variations for each of these data sets. Of course, there's Kitty. I'm just naming the most frequent ones, the ones you come across most often. And they're obviously they're much more diversified than just like 3 or 4. New scenes also a big one. There's different variations of caddy for cyclists, pedestrians. There's even like dataset complexity here, easy, moderate, hard. It's kind of funny. And yeah, Mask-RCNN, of course, also like towards the COCO subfamily, the tree of benchmarks. And there are lots of existing solutions, of course, as for these kind of old and classic traditional computer vision tasks. Many different architectures, lots of implementations of these architectures and approaches on GitHub, in any of the frameworks. This could be TensorFlow, this could be PyTorch, this could be something else. But most of them are, of course, in TensorFlow or PyTorch. Well, this is in Caffe, something very old and outdated, something very scary. I wouldn't suggest going into what Caffe is. So PyTorch, Caffe 2, yeah, sure. TensorFlow, PyTorch. These are like recent papers and their implementations, respective implementations on GitHub with sorted by stars. So these are just the stars on GitHub, and there's a date, there's like a short description. You can follow the paper, like YOLO. YOLO is classic. It's like literally something that works still very efficiently, in a very like fast manner, and it just is a conceptualization of the most robust and efficient one-stage detector, object detector. So you can just click on this like kind of snippet here and go into details. There's like a short. This is the abstract from the paper. So something that you there's even like different variations of the paper. This is how good this algorithm, this architecture is. There's like a CVPR 2016, the year of 2015 when this conference was held. They have separate paper from back then. There's also like a recent one. I don't know what the recent one looks like. Oh, maybe it's just they decided to duplicate it because this is the same paper. Okay, so this is a very considerably old scientific work, and they have a very nice catchy name. You only look once, or YOLO, and basically this is like a real-time, basically the most real-time object detection, especially for that time. Right now there are like some modifications to the YOLO itself, some different variations of other detectors, but still YOLO is like state-of-the-art, I'd say. And you can obviously read the paper, the PDF if you want. There are different implementations here, like even in Colab, on TF. What the hell is this? I'm sorry. What is that? I'm curious. Let me have a look. Oh, this is something Chinese, I think. Maybe no, it's not Japanese. Let me switch to English. Battle detection. What is this framework? They use some different framework. Something very non-Western. Kit structure, model performance. Anyway. What? I've never heard of this even, honestly. I mean, they're based on YOLO, blah blah. Efficient high development toolkit for optimization and paddle. Oh, paddle. Makes sense. This is like there is a variation of a Python library and C++ code. Like this is pretty much mixed that is somewhat unfamiliar to our lands, so to say, to like Eastern Europe, Western Europe, North America, but like state of the art, like most advanced researchers and engineers from the east, from the far east, they tend to use this tool, this framework for their implementation. Honestly, I'm going to be honest with you, I don't know much about this. The deep learning platform in China, there you go. I think they're variant of TensorFlow and PyTorch combined, I guess, maybe more optimized. This is like, there's a library, of course, normal one, a GPU-based one. But this is interesting. There's a guide in Chinese and English. Okay, anyway, we got distracted. So there are like different implementations of classical YOLO, all torch, TensorFlow, PyTorch, Cafe. What else is here? Anything else? Once again, paddle. You can obviously kind of get a feeling of the distribution of these like repositories. TensorFlow, PyTorch, of course they're exchanging, and there's certain variants, but if you like look up some statistics, most of the implementations now are like prevalently on PyTorch. The newer the implementation like date threshold, I mean in terms of like since which year they started re-implementing the paper, the more prevalent is the part for PyTorch, and the less for TensorFlow. Okay, so of course benchmarks back in the day on certain data sets and certain tasks. They have even different tasks. You can use object detection architecture for different conceptual like tasks in industry or in research and whatever. You can count objects with it, like detect and try to conceptualize how many like certain like people or objects that are living, could be animals as well, like street animals, have passed through certain like intersection through the road or something else. There's a real-time object detection, which is something that is going to be working non-stop on like CCTV cameras in the streets. Not CCTV, but like just security cameras. There's just simple object detection. You have a stationary frame, and you try to predict, to define what certain areas of interest, or namely objects of interest, are in the picture, in the frame. And they also have this, I never quite paid attention, but they have this very nice summary of tools and concepts used in YOLO. So they're using like one-by-one convolutions, which is like an architecture flowing from not VGG, GoogleNet, and ResNet for that matter. They have like some augmentations with color jittering. They have obviously convolutional kernels, dense connections. This is just a typical architecture. You can click on any of these and like get more details. Dense connections, just a prediction layer. That's about it. The final one, or linear mapping function. There's like dropout, a technique for regularization and making the network, the neural net, more robust and more consistent without overfitting much. They probably, yeah, they did like borrow some of the concepts from Fast-RCNN. I'm going to go into details in quite a bit on Fast-RCNN, but for now let's just leave it as is. There's leaky ReLU as one of the main activation functions. Basically, this is the usual ReLU, but with a slope, with a parametric slope here that just allows the negative values to be accounted for, and just a more advanced version of rectification. It was very popular back in 2015, 2016, maybe even 2017, but then people rolled back to ReLU or parameterized ReLU. You can read the theory on this method in the paper if you want to. But actually, it does allow for better combating of problems of vanishing gradient and exploding gradient even further. There's max pooling used right here. NMS is a very important concept for detection or non-maximum suppression. Basically, simply put, this is we have such a terrible picture here. I bet I can Google something much quicker than maximum suppression. So they have this. So the object detection mechanism predicts different boxes for this person for some reason. Just overfits, kind of, right? Makes more noise, puts more noise. This is even better example. So you can classify, like you can put the bounding box of the car like rectangle box that just signifies that this object is a car. But your model, for some reason, apparently thinks there are like multiple cars, different sizes actually, in the same spot on the frame. And to mitigate this, there's an excellent approach called non-maximum suppression, which, simply put, it removes all the redundant and unnecessary boxes and leaves only this green one, the most accurate one. And there's this algorithm, very exciting one. I used to code this myself when I was doing my first commercial project in CV in object detection. And basically, simply put, this also has to do a lot with like metrics or Jacquard index or intersection over union. And IOU is just, no, this is terrible. Intersection over union. It's just a metric that takes the intersection of two like bounding boxes, and then it divides it over the like the whole area of the union of two boxes. And this basically signifies the higher this metric is, like it can range from obviously 0 to 1, but the higher it is to 1, the closer it is to 1, the better IOU, the more consistent prediction we get from comparing the original truthful box or ground truth to something we predicted, or just the predicted box. So they say, like here, it's a good example. There's a poor IOU kind of because we have too small of a box than we predicted. The red one is not great. Or actually, no, never mind. Let's say red is like our ground truth. So the green one is too big, and unfortunately, the IOU is like 40%, as they mentioned there. There's a very small intersection. There's a good example of IOU, which is like 73.3%, but you can see still it's not perfect. The boxes slightly shift in different diagonal corners. And in the end, there is an excellent intersection of union metric example with IOU of 93 almost %, and they kind of like almost align one on each other. So this is a very important concept to understand for both object detection and for non-maximum suppression. And yeah, this was as simple as brief of an explanation on IOU and Jacquard and NMS that I can explain. I can come up with. This basically has the algorithm itself in NMS just compares the boxes, keeps track of like what is the most optimal IOU between each pair of the boxes. It could be slightly suboptimal, but people from the point this algorithm was created, they managed to modify it even further and reduce the computational complexity if we have like a very big amount of boxes on one like potential object, like 1000. So that we don't need to perform any unnecessary calculations, because the more data, the more computation, the more expensive it gets, the bigger problems we get. So this is another important concept for object detection and Slick-Urilu and NMS. So obviously the very usual one more important thing for NMS to work well, you have to discard everything, all the boxes that do not have intersection over union greater than or equal to 0.5. So anything below 50% is kind of like useless, and that makes sense. You can also set this threshold to higher, like 0.7, like I did back in the day, for certain tasks and for certain scenarios. But this is like something that you can tune the parameter. Yeah, randomized resized crop. This is more augmentations, data augmentations to enrich the detector dataset size. There's an original ReLU also being used. There's an RoI pooling method, which is something of a novel concept, just a region of interest pooling. And it tries to extract like small feature maps by a large kernel, kind of, they think it's a small one. And this thing is kind of like a concept borrowed from Mask-RCNN or FastRCNN. And they kind of like try to condense the information from the feature maps and predict in a more classical machine learning way the potential areas of interest where the object might be. I'll show once in a sec. I'll show in a picture from my notes. So yeah, it's sort of RoI. In essence, RoI is like a pooling layer is max pooling, but we do it on a discrete grid based on a box. Yeah, so it takes into account these are rectangles of interest. Yeah, the optimizer that they use is GD with momentum, pretty classic, something that's state-of-the-art nowadays. Softmax as the output function, activation function. There's away decay even used, I didn't know that. Shame on me. The step decay, yeah, probably they did use some away decay in YOLO, I didn't know it was step decay. And this is kind of like the original architecture, YOLO v1. You can have a look at YOLO v1. So, just I'll take this brief example of one architecture, and I'll kind of pivot into details on all the necessary modules like NMS, IOU, Jacquard, activation functions, and then I'll go into architecture and we'll kind of like wrap around the whole like task of object detection on the example of one of the greatest architectures here so far. And basically, as you can see, so it looks very similar to this like traditional convolutional neural network, and it has like some large kernels, 7x7. I understand those are very inconvenient, I guess, to use nowadays, but back then it was fine. So they have basically 24 convolutional blocks, blocks like layers. They have certain blocks here, 1, 2, 3, 4, 5, 6, 7. So 7 blocks, each consisting of something like 3 or extra layers, and that basically they are followed by 2 fully connected layers here in the end, where they just linearly map the neurons, flatten them, and then they reconstruct like something that is known as the output of YOLO. They also, yeah, they're like stressing out that they use 1 by 1 CNN layers. And they achieve reduction in feature space from preceding layers this way. A kind of smart technique, even for that time. Of course, they use a pre-trained variation of like these. They do not explicitly retrain the 7 blocks of 24 convolutional layers. They just use the pre-trained weights on ImageNet from ImageNet for classification, namely, and use the same resolution for the input 2 to 4 or 2 to 4 3-color channels. So it's very basic explanation how this works. Just you would ask me potentially, how's this different from a CNN? Where's this generate the potential boxes part? Yeah, for this you need to go in the paper. There's this architecture. There's this old paper. They're so short for some reason. Now papers are quite long, and I'm just basically kind of surprised was the page size comparison is so drastic. Yeah. So just going into details, there's a comparison, but there's limitations of YOLO. This is the in details description, namely, like some parameters that they're using for training. Well, let's go to architecture, network design. Yeah, so they do have this unified detection, which basically means they do not need to go through 2 stages of detection. They only need to go through 1. And what does that mean? Yeah, let's pause here. I'll explain the conceptual difference between all the detectors. So this is something new. Let me see. So conceptually there are 2 types of detectors, 2 kinds, 2 separate classes, big ones. The 2-stage detectors and 1-stage detectors. What's the difference? Let's start with the 2-stage detectors. So it's going to be simpler to explain. The 2-stage detectors, bright examples are here. RCNN, Mask-RCNN, no, let's go one by one. RCNN, Fast-RCNN, Fast-RCNN, Mask-RCNN, Faster Mask-RCNN, and this is kind of like the one family of models, architectures. There is SPPNet, kind of like an advanced thing that arrives a bit later, and FPN, which is a feature pyramid network, also kind of like has some different concept and getting the regions of interest later on. So very briefly, these have 2 stages, obviously from the name. The first stage is they perform a very typical and traditional convolutional just they convolve the input images, and they produce feature maps like a CNN, like a typical CNN. But because they do this, and they do not have a specific mechanism attached into simultaneously in the end, in the same time, to produce the bounding boxes, the predicted bounding boxes of the objects, they require a second stage. A second stage is a region of interest pooling, generation of regions of interest, like certain areas that might be potentially fit for the candidates of our objects, of the bounding boxes that we predict. And basically, this forces the network architectures, these ones, to function in two levels. And if you do this, you kind of split them in halves, and you need to kind of fuse them together. And in practice, in reality, whenever you do come up with an architecture like that, it usually functions very poorly on inference speed, because it takes more time to, the second part of the network cannot function until the first part of the network is done. And there was an insanely terrible bottleneck for these models. And this is why they're not dominating the one-stage detectors. Bright example is Mask-RCNN, a very classic model, which performs like both. Can I add a note here? This is both object detection plus instance or semantic segmentation. I have not talked about segmentation yet. This is a more elaborate task in computer vision. We'll focus only on object detection for now. So as you can see in this picture, this is a very good demonstration. And there's an image input in the bottom, and you pass it through this large chunk of convolutional layers and blocks, and you generate feature maps. And once you kind of like have the sufficient number of feature maps, then you have a separate module, a second stage, which is called RPN, or Region Proposal Network, which kind of proposes, obviously from the name, predicts the potentially good fits for our future boxes. And then we have these proposed regions on the feature map. We extract the whole feature map. We kind of like intersect them again back in this last piece of the plot on the figure. And then the region of interest pooling is performed. Namely, the classifier is awaiting the regions that can be like finalized and constitutionalized into like the most relevant candidates, and in the end, like the bounding box is getting addressed. Don't mind this. This should be deleted. Yeah. This is how the RPN works, the region proposal network here from this side. It's like a classifier and a regressor. It's like, so that you understand, detection is quite a sophisticated task. It involves previous knowledge in many different applications and tasks, namely like classification, regression, also like anchors that come into play, not here concretely, they are used here, but more likely in one-stage detectors. Yeah, they just what's happening on this image, on this figure, is they have like this convolutional kernel that slides over the window and produces some intermediate outputs, and then those are getting split into scores and coordinates, and then the anchor box kind of like has done its work. It's produced a potential proposal for the classifier, for the RoI pooling step and the classifier later on. This is some heavy theory coming back from like even AlexNet extensions, but this kind of works well in practice, robust, nice, and decent, but it's very slow on inference. It's a very slow model to train. It's even a slower model to like introduce into a real-time scenario. And there's of course one-stage detectors, something that's state-of-the-art nowadays. People have been refining these very much. They use a very important concept of an anchor, which we already kind of briefly had a peek at here, this image. The anchor basically is a predetermined. We have a predetermined size and ratio of these boxes that is going to be generated. Not generated, just simply we have an image and we want to slice it like a cake, not a cake, but like a pie. We have like this rectangular pie and we want to make slices. Like if your relatives, like your parents or your grandparents who have ever been making a pie, that's like the way you slice them, like the pie that is a rectangular shape. You do this kind of in a similar fashion here with a pseudo bounding boxes, like this wide net or like an intersection of lots of different lines, and you assign to the center of each pseudo bounding box a center point. And the center point basically is the center of each box and is called an anchor. And this is basically a very cool technique used to detect different images, different objects in the image, sorry. This is Retina, this is something more advanced. SSD is something more simple and outdated ever so slightly. But let's get back to YOLO, like to actually finalize what we've been reading the paper for, because from this paper, honestly, from 2016, it's not, even for me, it's not that like obvious how to make out the summary quite quickly. So YOLO, of course, look one's architecture. This is a better image that I had from long ago for describing the architecture. There's the same kind of flow for the input image, the convolutional downsampling, like 1, 2, 3, 4, 5 CD blocks. There's also DC block, one simple dance connection. This is a novel approach. Basically, it just connects all the layers and gets information from across every single step of the feature map production process, helping to mitigate the need for a second stage. So just in the process of kind of like working through the image, the network receives and interconnectedly receives information from each and separate part of these modules, blocks of convolutions, with the help of dance block. It's even a part of some architecture that they used here. Basically, there's a dense connection block that makes sure we have like this intermediate information throughput. There's a spatial pyramid pooling block, which is a more advanced feature. Basically, it just disassembles the feature maps into different pyramidal shape-like interactions. It has different kernels, as you can see. I don't know if you can see, but I'll try to zoom in. There's a 5x5 part here with the kernels. There's a 7x7 and a 13x13. But then they kind of like pull them together and enrich them into like 13/13/512 feature maps each. And then they stack them together and like receive something like 13/13/2048. I don't know all the specifics and details, but it's like the details and the specifics according to the paper and the plots and figures they provided. And then in the end, there's this object detection block. This is 13x13 by 1024. This first yellow block in the end is like a fully connected part, but still it uses some kernel apparently before that. So yeah, 3x3. And in the object detection block, this is the final output of the model. There's the same, the feature map dimensions are the same. And the only difference is I have these parameters K and C. And K and C, those are, I need to delete that as well. They're just the channels and a certain predefined ad hoc hyperparameter that defines the number of feature maps, especially the ones that kind of like got the pre-processing right. And there's like a 1x1 kernel, and then finalizes the predictions and regresses the boxes. So yeah, there's this summary here. We have lots of anchor boxes of different sizes and scales. We try to see if anything is matching the ground truth. So something that we have a labeled data set. We have like ground truth boxes, like coordinates, a center point, and like width and height, for instance. That could be one interpretation. The other interpretation could be like the lower left coordinate, the upper right coordinate, and the center. Something like that. And basically we compare the ground truth. We kind of like ad hoc, like blindly try to overlap each anchor box with the ground truth and see if anything is closer to like the center of the object. And once we got all the candidates here, this is what happens in the object detection block, like throughout the whole sequence. The NMS is applied, the non-maximum suppression. Remember the technique, this one. And basically it just removes extra unneeded boxes that overlap too much, and in the end they use a clusterization algorithm for synchronous clustering. This is like a pre-processing step for the output. Oh my god, what is this? Ridiculous. I'm sorry, this probably has to go as well. Anchor free detectors. Yeah, this was quite kind of like a lot of information, a lot of to digest, but this was a very brief overview of like two most important kind of like rival architectures in back in the day, object detection. So YOLO and the Mask-RCNN, the ones we looked at here, this kind of approach with the two-stage. The difference here, Mask-RCNN, there's obviously a faster CNN as well. But the faster CNN one only performs object detection. It does not do it doesn't perform instant segmentation or semantic segmentation. Instant segmentation, for your understanding, is just a task of kind of like object detection, but more sophisticated object detection, where you kind of want to find each object. Like this is a bounding box, but you need to like select a mask of this object to signify the borders of it and to kind of like outline specifically where the regions for this object start and end, and every single pixel, just regress pixels. This is a more complicated task, and we'll look into this later in later weeks. Good. Are there any questions pertaining to what I just been explaining from all this YOLO and Mask-RCNN and all the modules? Okay, no questions. Still have some time. I won't be occupying too much of it though. So let's have a look at the state-of-the-art stuff. So there's maybe there's something different. Like anchor-free detectors. It's a separate paradigm, completely separate story, very advanced one. There's also a adapter. Let's have a look at your home task just for a quick overview. You have I have explained YOLO. I have explained faster RCNN. Basically, faster RCNN is a worse version of Mask-RCNN, and YOLO v4 is just YOLO, but just more modern. More modern comparing to YOLO v1. And there's adapter, which is you'll have to find out on your own or like on the lecture. Adapter, like very briefly, it's like a transformer-based detection. It's a very cool concept. One of the earlier applications of transformers, transformer-like modules at least in computer vision, that came from NLP. And there's this big, very unreadable, user not friendly paper with lots of pages, and they have this, like prediction head, transformer, encoder, and decoder, like a full architecture. This is very kind of ugly, but pretty good performance, I guess. This can be used for like instant segmentation, semantic segmentation, I guess. Yeah, not bad, not bad. So in your homework, you need to compare these three networks. And you don't need to like write any code or perform any like modeling. Just simply open the papers, or just papers with code if that's more like you, and have a look at the following characteristics. the size of the model, or the number of parameters, the speed of the model on a single image, or the inference time, and of course have a look at the architectures, the conceptual difference in architectures. Well, obviously, it kind of like pretty much almost explained the difference between these two. And all that's left for you here is to study a little bit better, and study that a little bit, and just make like a more precise conclusion. What's actually the difference between these three? But from what I just kind of like sneak peek to you, this is like transformer-based architecture, and kind of like that's the answer as well. So kind of like a first task done for you. But still, you can feel free to delve as deep as you want on this one. This is like 3 points, and there is also one for 3 points. The second part, a more practical one, is kind of like a creative task, and involves you taking shots. No, perfectly ideally. We do not force you, of course, but it would be nice. It would be cool for you to do this, to take pictures with your phone and camera. Like different objects, different angles, same objects, different angles, different different lighting, maybe some other variation of like your ideas. You can be creative here to see how like modern models work on pre-trained models work on these your taken by yourself images and pictures. And there's also so you take like, I don't know, 15-20 photos, as much as you like. You can do more, you can do less. You open the tutorial in Colab, and you're asked to just run the inference of the model, of the detection model on these images, like with the Detectron 2. This is here. There's a tutorial here. There's completely user-friendly. You just have to click through all these Google Colab cells. Like if something does not work, you'll have to figure it out, of course, but I think it works. It's just very brief here. So just load an image. Of course, don't forget to do the login here. They don't log in here, so so you need to basically kind of I'll not touch this. Wait, is this authored? I think so. So you just need also, for your convenience, it's up to you, of course. You can import things from your Google Drive, or like manually upload the images here. But I'd advise you, just for the practice for the future projects and assignments, there's like this upload button. You can upload stuff, but it only will stay here as long as the session lives. Once the session dies, it just disappears, evaporates. But if you want the things to stay here for a longer time, like for each time you relaunch the session, you are pretty much, you write something like from google.colab import. No, I don't remember. Google auth. There is that a word? Yeah, like something like that, and then you authorize. You attach your like Google Drive storage to the notebook, and then you kind of like have all the images, you know, all the paths, because like it can be tricky to actually intuitively from the first try understand what this directory is. And believe me, this is not a joke, because if you go up, you get into this hell of lots of different Linux-based packages and folders. And how do you find the previous folder? I don't even know. I don't think it's bin, of course. It might be something like no, not TMP, not run, not root. See, we already kind of lost the game. etc, no, dev, no. So yeah, this becomes challenging. Maybe it's user. No, not even user. So yeah, be careful here. All you need to do is run through all these things. Just load in the image like this. No, not like this, but just you can simply forget about this line of code and just straight ahead read it with CV2, and just make sure the image is fine. Then we create in Detectron 2 from Detectron 2 default predictor. So you just do all this. You can, of course, change. You don't need to change Coco instance segmentation. This is fine. You need to. You are free to experiment with different models. This is Mask-RCNN. on ResNet 50 and FPN3. This is kind of like a mixed model. You can try to like Google up Cockit, or just go into, it's going to clone GitHub repository. See, obviously from model zoo get config file, this model zoo thingamajig from Detectron 2. So you can just Google up Detectron 2 model zoo, and just go into model zoo, I don't know, GitHub probably, and find any model you like. ResNet, this is a faster RCNN and different backbones. There's inference speed, of course. See, even like tips for you how to solve the first homework on the speed. RPN, faster CNN, segmentations, panoptics. Yeah, I just need the first part, just I guess faster CNN, Coco object detection baselines. Retina. I don't think they have YOLO for some reason. Weird. But yeah, just you can experiment with these. You can leave everything as it is here. Just create the model from the YAML file. Don't choose. I mean, you're not like you don't have to choose different parameters for this threshold. The 0.5 intersection over union cutoff. If you know what you're doing, you can do more or less. Less is very dangerous though. There's a checkpoint that you load, of course. Just predictor. Create the object, outputs, run through the predictor. It runs for a couple of seconds, and then predicts the boxes and the classes. So it predicted quite a bunch of things here. Let's see what's happening. And then just use visualizer to CPU, blah, blah. You have like a, what? Oh, that's an umbrella, is it? Oh yeah, it is raining actually. But there's like a bunch of umbrellas here. Only one actually. I see 1, 2, 3. Good. A couple of people. This big horse, and yeah, there's also a backpack with a 58% probability. Is that a backpack? Yeah, that looks like a backpack. So this is how you inference the images. This is all you need to do. Like run through on 20 images, and show the results of the detection. Comment on the obtained results. So perhaps you see that there's been a false positive or a false negative, and you kind of like should express your opinion to as why that happened. Namely, why did the model work poorly in such condition or with such architecture, etc., etc. I'll not be opening the submissions for now, but no worries. You'll get additional time for this part, I guess. We'll see. This is for object detection. Yeah, so I explained very briefly as for the task itself without showing the actual lecture. I'll leave it to Dr. Schwei, Dr. Nadia, and the only thing I did is just open this section here so that you have a look on the task and the lecture if you want, of course. Yeah, I guess that's it. I guess that's almost our time. Usually try to keep the practice periods short. Any questions? As for yeah, sorry, I have not seen your hand. Please go ahead, Pavla.
Question: do we have to work in Google Colab all the time? Because not like do the average laptop, from your experience, have the power to train a model for such tasks as object segmentation, or we should always use Google Colab or similar services?
Well, that's a very good question. It depends on the laptop, of course, not on the hardware on it, but usually deep learning, especially like even the tasks like classification of images, but especially the tasks as of segmentation, any kinds of segmentation later on, and detection, those are quite compute heavy because they like try to brute force lots of those anchor points and just align and perform NMS and etc. etc. This could be resource draining, I guess. Depending on your laptop, of course, I would always suggest using your local hardware, not using the Colab because that's a bad practice in my opinion. you don't, not only do you not like get the full feeling of the pipeline, but you also kind of get used to that helper coming out in the form of AWS or Google Colab or something like that. But if you don't have, of course, the luxury of performing the calculations on your device, it's highly advisable to actually do use cloud services. How do you differentiate? How do you define if you can train the model? Well, you have to, like, if you don't have the prior knowledge to how fast each model is trained, especially on the how big an amount of data, then you can have a look at the paper and then extrapolate from there. They usually indicate what resources they were using, how much time it took, and what's the data set, and what's the architecture. If you're using something less of, if you use less data, if you use like a simple model, if you use even for object detection task, like I don't know, a small portion of like COCO data set, and you have an okay-ish CPU even, or like CPU probably would require a very small data set. GPU, a decent GPU, an okay-ish GPU, like average below average GPU on the laptop, this should be fine. Suppose, yeah, given the fact that you have a limited computer on the laptop. If you have something better than that, like something quite okay that's considered a good GPU or something else for not modern standards, then by all means go for it. I personally just one last thing to add is I personally have different resource options. I have like, not only do I have different each and every single kind of OSs, like both Mac OS, Ubuntu, Windows 11. But furthermore, I do have different devices on each. I have a 1650 Ti on my laptop, which is like a working laptop on Unix, like Ubuntu. There's a GTX 3060 on my Windows 11 PC, which I'm on right now. I use mostly use it for training, like this on this very specific. On some specific models that are very hard to train, but most times they're not. I actually do not like shy away from using Colab. I basically did all my job, all my work and hard research and all the engineering and modeling for the Toronto research program, and kind of like submitted a paper only via TensorFlow, via Google Colab. And the reason for that was Google Colab supports TPU, which is a tensor processing unit, which is like twice as fast as GPU, and like of the same power, of course. And we had a lot of images we needed TPU, we wanted TPU. It was easier to inference and to convert the model into a TF Lite after that. So that's kind of like the forced choice. If not for that, I would probably refrain from that and just do everything on my PC. And also, it depends on the sensibility of data. If your like client or future clients just have restrictions that you can't download anything on your local PC, even like on the working one, especially on the working one, they provide you a poor laptop, then it might be a problem, and then you have no choice but to go for cloud services. That's about it.
Thanks very much.
You're welcome. Any other questions? Okay, good. I suppose no questions. It was a big pleasure to share some information and insight on the object detection with you today. You will have the lecture next week and the assignment, the proper practice period with me on the detection, maybe something else next week as well. Feel free to like ask away any questions like in Slack or on Telegram if you are struggling with the homework. And I wish you a very pleasant Friday, as well as great weekends and Halloween. Cheers and goodbye, everyone.
Thanks. Bye.